Okay, so this will be our first lesson for our last unit. Like I just said a few seconds ago, today's topic, tomorrow's topic, and Thursday's topic are there's no math equations to cover. If I could actually, I always throw a slide in my notes here that just shows you a formula sheet. And if I could, I'd actually like to point out that we've covered pretty much every formula on this sheet. There are two left that we haven't covered. You guys would have done kinematics over here last year in Physics 20. Dynamics, also Physics 20. Most of these equations right here, let's see, those ones there. These equations here would have been in Physics 20 as well when you'd covered them. In terms of stuff that we've covered this year, over here's a couple of the momentum equations. This was like the big bulk of our middle unit when we talked about forces and fields in terms of electrostatic forces, magnetic forces, like this formula F equals ILB. The more recent formulas that we've learned, all of these ones right here are to do with waves. When we talked about refraction and diffraction, interference, these formulas over here were formulas that we learned about in the more recent unit, like the energy of photons. We also covered this formula, and the top one really relates them. This is energy is based on momentum and speed of light, which is basically this formula right here, along with this formula right here. The only difference between energy and momentum is it's Planck's constant over the wavelength, but this one has an extra c in it, which is why this one has an extra c in it. This one's the Compton formula. Long story short, what I'm trying to point out to you is that there's only two formulas we really haven't covered. This one up here, E equals mc squared, Einstein's famous formula. And the only other one on this sheet that we really haven't covered is the bottom one down here, which is it's a half-life formula, which most students find very easy if they've taken a 30-level math course, which I'm sure most of you have. Because if you know how to work with logarithms, this is going to be really simple for you if you've learned how to do half-life in 30-1. So that's it. We're done math equations now. So like I've been saying for the last little bit, most of what you need to now know is theory, scientific contributions, those sorts of topics. Less than half of your diploma involves calculations. Like 40%, I believe is the number they said, is how many questions will actually require a math calculation. So that's why I think it's valuable to do that timeline. Okay, anyways, let's get started. So we've been talking social studies kind of stuff, history, who did what when. At the turn of the 20th century, so in the year 1900, physicists were at the point where they were patting themselves on the back saying, good job, everybody, we got physics figured out. And I love this story that I've got at the beginning there here. Max Planck, who we now recognize as being a fairly influential physicist, because he's the one who kind of came up with the idea of quantizing energy, recognizing that energy must come in like packets. Anyways, his high school guidance counselor type person, he was debating between whether to go be a musician or whether to be a physicist. And his guidance counselor, whoever that role would have been in the year 1900, said, you shouldn't go into physics. There's no future in physics. Physics is like a dead end. Don't go into sciences, go into the arts. And I think that is hilarious because nowadays, if you were to be debating between going into the fine arts or the sciences, I think almost everyone would push you into go into the sciences. The fine arts are really hard to make it in, right? And it was the opposite at that point. They thought there were limited job opportunities because everything had been discovered. And at least according to this, funny little anecdote, I mean, how cool is that Max Planck is the one who basically blew open the doors and people started to realize that there was a new world of physics, the quantum world, the atomic world of physics. So I really can't say enough about how Einstein, Heisenberg, de Broglie, how this word really here is probably understates it. They revolutionized the field of physics because as soon as they introduced the idea of quantum physics, which is basically a fancy word for things at the subatomic level, it gave them something new to study. I've given you this quote by Feynman before. These scientists, they could not explain what they were discovering. To be honest, I'm not even really sure that we still can explain why things happen the way they do. We definitely can explain what is happening. Physicists know what is going to happen in quantum physics. They're just not really sure why electrons decide to behave as a wave, and then as a particle, and then if you look at them, they behave differently. And then if you close your eyes, they behave differently. And it's like, that makes no sense. That fact that like if you observe an electron, it all of a sudden behaves as a particle. And if you stop looking at it, it behaves as a wave, as though like just the mere presence of you closing your eyes changes the outcome. That makes no intuitive sense. So anyways, getting past that, one of the coolest things about the implication of quantum physics is how it's affected chemistry. And our final unit has a huge overlap with chemistry. We're basically going to discuss how chemists learned what they have about chemistry. Some of you guys have taken Chem 20, Chem 30 at some point. You've probably learned about, protons, neutrons, electrons. If you guys have done physics or chemistry 30, maybe you've done Leo says GER, if you know what I'm talking about for that. Like loss of electrons is reduction. No, loss of electrons is oxidation. Gain is reduction. Physicists wouldn't have known, chemists wouldn't have been able to do that stuff if we didn't even know about electrons, right? And so the discovery of subatomic particles is my title today. This has really helped chemists out a lot. And so you're going to be asked in this course to do a rudimentary, like a basic amount of chemistry. And that's why I gave you guys a basic periodic table. We're not going to use it necessarily today, but in the future you will be asked to talk about protons, neutrons, electrons, and just the basics of how elemental chemistry works. So, okay. Anyways, let's talk about our timeline, because that's really the goal of today. I need to let you know about 3 scientists. We're going to do 3 of them today: Dalton, Thomson, and Rutherford. Tomorrow, I'm going to ask you guys to watch a YouTube video on the Bohr model. It's already posted, so if anybody wants to watch the YouTube video, you can already. Otherwise, the goal is to watch that in class tomorrow. And then Thursday, we're going to talk about the quantum model. And we're going to build a timeline about how chemists not so much physics, but I mean, it's so interrelated at this point, they're kind of the same thing. But really how chemists have now learned about the internal structure of atoms and how they can use that to understand chemistry better. So you probably know these names because you're supposed to learn about them in grade 9, I think. So, but I'm going to give you a little more details than you learned about in grade 9. So we're going to start back in 1803. 1803 is one of the first main timeline points that if you do make a timeline for me, like a Prezi or a PowerPoint, you're actually going to want to start around here. There were 2 major, accomplishments or discoveries around the turn of the 19th century. One is this one, John Dalton. The other one, by the way, was Young's double slit experiment. You guys remember the double slit experiment where not where he shot electrons, but where they shot light through the double slit? That was in 1801. This is 1803. So John Dalton presents his idea. He suggests that everything that was an element on the periodic table, so hopefully you guys are familiar with the periodic table a little bit, right? We're talking hydrogen, calcium, neon, strontium, all that sort of stuff. He suggests that if it's an element on the periodic table, it's made of something called atoms. And he thought that they were indivisible. Literally, the word atom, if you've never heard this before, comes from the Greek word atomos. That's actually like the root word of atom. Atomos is the Greek of it. And literally the Greek word means indivisible. So John Dalton has this epiphany. He suggests that, hey, there's all this stuff that we're learning about on the periodic table, hydrogen, oxygen, nitrogen. He suggests that if we could zoom in on it with a microscope that was that small, which granted they didn't possess, right? Like they didn't have a microscope that could see atoms at this point. But he suggests that if we could, there's going to reach a point where you cannot cut something in half. The analogy I might give is imagine that you have, like a dessert, like a cookie. And what you want to do, hey, fellas, can you shush? Thanks. You have a cookie, and you might want to cut it in half, and cut it in half again, and cut it in half again, and cut it in half again. And those of you who are in calculus recognize that what I'm discussing here is a limit, where in theory you could cut something in half an infinite number of times. John Dalton suggests, no calculus going on here, guys. There is a limit at some point here. You cannot cut this thing in half, and elements, atoms on the periodic table, that's as small as it gets. That's his suggestion. And to be honest, it's not a horrible suggestion. He wasn't right, not by any means, but he had this idea that matter was made of atoms, and he called it his solid sphere model, where sometimes if you see a picture of it, it more or less looks like a billiard ball is often used. The idea of it basically just being this ball. We still use that in chemistry to this day. Any of you guys work with like model kits where you have these like little balls and sticks that you use to make models. We still actually use John Dalton's model of the atom sometimes when we try to draw molecules. So it wasn't a horrible idea for 1803. Keep in mind, he had no technology at his hands whatsoever. But he had a problem. He was unable to explain how they were able to bond. Does anybody know why he was struggling to explain how they were able to bond? What do we believe bonds in chemistry are made of? Electrons. Well, and not just electrons staying in one spot, but electron cloud fields that are orbiting and or overlapping in something we call orbitals. We're going to talk about that more if you're not familiar with it, but at the time he couldn't explain how they bonded because he had no clue that subatomic particles even existed. So it wasn't a bad theory. That really lasted though until 1897, I believe is the year. 1897. When J.J. Thomson began experimenting with something called a CRT. CRT is a short term for cathode ray tubes. And what he basically had set up was a vacuum with 2 electrodes at each end. He was messing around with a battery. And he found a way to make, on one side of the battery to the other, he found a way to make electrons jump. Honestly, this is basically the same thing as like the tube that the photoelectric effect experiment was done inside of. He was making electrons go from one end to the other. He didn't know they were electrons though. He called them cathode rays. And the reason he called them cathode is because they were emanating from the cathode side of a battery. They would always move from the negative to the positive. You guys kind of familiar with the idea of anodes and cathodes in chemistry, those who've done that? Anodes are usually considered to be negative, and cathodes are considered to be the positive poles of a battery. And so he called them cathode rays because of where they were heading towards. So he didn't know this at the time, but his cathode rays were actually electrons. And what he was doing with these particles is he was trying to deflect them using an electric field. And I'd like to show you some diagrams of what he was trying to accomplish on apparently not this slide here because there's no diagram there. That's weird. You guys have pictures in your notes there, right? For those of you who printed off notes, there's a picture there, right? That is weird. I even have the picture here and it's not showing up. Okay, hang on a sec. I'm just going to reboot my notes. That is weird. If I don't have those pictures, that's kind of a waste of time here. There we go. Okay, here, let me pick this up again. Sorry, I don't know why the photos didn't show on my notes. That was really strange. This is a kind of schematic diagram of what we would call a cathode ray tube. So here's what he ended up doing. He ended up using a hot filament to eject electrons. And as he heated up this filament, I mean, he didn't know it at the time, but he was effectively causing the photoelectric effect to happen. By adding enough energy, he was able to free off electrons. It wasn't necessarily light that was causing the electrons to be liberated, but by heating it up enough, he got the electrons to move. But can you see right here how he's got a voltage going on? He's got a negative and a positive plate. We've already talked about what happens when you have a negative and positive plate. If you have an electron, now granted, he didn't know these were electrons, but if you were to have an electron, the electron would want to go away from the negative plate towards the positive plate, so away from the anode towards the cathode. And so therefore, as it was leaving this cathode right here, he called it a cathode ray because the last thing that it left was the cathode, right? You know, anode and cathode of a battery, right? It left the positive side of a battery right here, and then the electron was sped up and shot through this vacuum tube. Now, normally what would happen is if you didn't do anything to this particular electron, it would just go on a nice straight path, this black one right here. But Thomson was curious about what these small little particles were, these rays were. He didn't know that they were matter yet. He didn't know that subatomic particles existed. He thought that the smallest thing that existed in the world were the elements on the periodic table. So in terms of like decreasing size, lithium, what's before lithium? Helium and hydrogen. He thought those were the smallest things in the world. He just thought this was a ray of something, probably like energy. He discovered, though, that he could play around with electric and magnetic fields. And just like we've learned about in a previous unit, here's what he tried doing. He put a positive plate, say, on the top, and a negative plate on the bottom. And what happened in that case is that when he turned that voltage on, this negative electron, which again, he didn't know it was negative, it caused the particle to deflect in an upwards direction, because wouldn't a negative electron want to become slightly attracted to this positive plate? And so he thought that was kind of fascinating. He also messed around with magnets. He took these rays of electrons, again, not knowing that they're electrons, and he took these electrons and he put in here a magnetic field. These X's right here refer to a magnetic field going into the page. And if you guys remember your hand rules, if you take your hand, put it into the page, your thumb would be the original trajectory of the electron, your palm would force it downwards. And so this diagram right here hopefully illustrates what he was discovering. As he basically just played, he discovered he could make the electron either go up with an electric field or go down with a magnetic field. He then discovered, hey, what if I play with the electric field a little bit? What if I play with the magnetic field a little bit? What if I can get these electrons to go straight again? Because, I mean, weren't they going to go straight in the first place? So turn on the electric field, they go up. Turn on the magnetic field, they go down. Turn them both off, they'd go straight. Or turn both of these fields on, he makes them go straight. And he basically put together this equation right here. If they're going straight, it would imply that the electric field and the magnetic field were the same as each other, if they're going straight. He knew the formula for the electric field, though. That had been long since discovered. So electric force is field times charge. Magnetic force was charge times velocity times magnetic field strength. And what you'll notice in this particular example is that charge cancels, which is really good, because scientists didn't know the charge of electrons at that point. Okay. I've got this later on in our notes, but the charge of the electron wasn't discovered until 1909. And in terms of our timeline, this was 1897. And so although he didn't know what the charge of these small little microscopic rays were, he knew that it didn't matter. He could cancel that charge, which left him with this formula here. Field strength electrically equals its velocity times its magnetic field strength. And if you then divide by the magnetic field strength on both sides, he finds a formula for velocity. And he called this his velocity selector formula, which meant that he now knew how fast the electron was traveling as it went through this vacuum tube. Again, didn't know it was an electron, didn't even know that it was matter at this particular point, just thought that it was some sort of ray of some kind. So, what he was able to do, though, if I can go back to this slide right here, is that these negative charges, he thought they were cathode rays. He then started to figure out that maybe these things actually, maybe they weren't some sort of just form of energy, maybe they were actually forms of matter. And he decided to try to find their charge to mass ratio. Even though he had no way of figuring out their mass, and even though he had no way of figuring out their charge, because that hadn't been discovered yet, he realized that maybe he could find out how much charge to how much mass existed in these particles. Okay. And so that's what he did in this slide right here. After Thomson had determined the velocity these electrons were moving, he then turned off his electric field. And so that meant that he only had the magnetic field. What would happen if I go back in this diagram right here? What would happen right here if you were to turn off the electric field? Well, the magnetic field would deflect them downwards. But what would happen in a magnetic field is it would eventually make them to start turning in a circle. And he was then able to make his particles, as they started getting deflected downwards, he measured the radius of them traveling in a circle, and he put together these formulas right here. The magnetic force would then be equal to a circular force. Magnetic force is QVB. The circular centripetal force is mv squared over r. He was then able to cancel off one of the velocities on both sides of the equation. He was then able to take this radius right here, this velocity right here, and this magnetic field strength right here, put them all on one side of the equation, and solve for a charge to mass ratio, where he didn't know charge or mass. but he was able to calculate that there was a relationship between how much charge these particles must have had and how heavy they were. And here's where this is really important. He discovered that these must be low mass, highly charged particles. They actually had a charge to mass ratio that was 1,000 times less than the previously smallest known particle. Chemistry-wise, what's the smallest known particle on the periodic table? Hydrogen. What is hydrogen made up of? One proton and maybe an electron? Well, they knew about hydrogen ions. If you know a little bit about chemistry, you know about ions versus atoms. Okay. Hydrogen, written like this, would have one proton and one electron. Hydrogen plus would literally just be the proton. Give me 1 second, I'm going to close that door. And so at the time, chemistry-wise, the smallest known particle would have been a hydrogen ion. And a hydrogen ion was essentially a proton. Well, what Thomson discovered based on the charge to mass ratio is that the mass and charge here, it was actually 1,000 times smaller in terms of what these cathode rays were, which we actually now know. In hindsight, we recognize this. What is the charge of an electron? 1.6 times 10 to the minus 19. What's the charge of a proton? Also 1.6 times 10 to the minus 19. But what is the mass of a proton or an electron? Well, the mass of a proton ends in the minus 27, but the mass of an electron ends to the minus 31. And that differs in terms of the mass values between a proton and an electron. That differs by basically 1,000 units, because each one of the minus 27, 28, 29, 30, that's 10 units different. And that's what I've got on this next slide right here, basically, is that he realized that his charge to mass ratio was so much different than anything he'd ever discovered before for ions like hydrogen or calcium that they must have been super concentrated. He realized that there must be something even smaller than an atom. If an atom would be the periodic table, he realized there must be something smaller than even that. And he gave this name, this is the weirdest name in the world, he called them corpuscles, is what he named these particles. Originally, he called them cathode rays, and then he later changed the name to corpuscles, and he called them these really tiny, dense subatomic particles. We've changed the name from corpuscles to electrons, which I think is fortunate, because corpuscles is not a very, I don't know, it doesn't sound a very attractive name, corpuscles. So, anyways, he then believed over time that atoms were not indivisible. He came to believe that atoms must be made up of smaller particles. And he created a new model of an atom. And this is something you guys need to know for theory-wise. He came up with what he called his plum pudding model. You've probably seen this before. But the way it works is that he suggested that there must be these negative bits inside of an atom. And these negative bits, the evidence he had for it, was the fact that he had these corpuscle like particles that he could then deflect. And he knew that they were exceptionally tiny because he found the charge to mass ratio of them. So he knew they must be smaller than the smallest everything discovered up till then, and this led to his plum pudding model. The basic idea behind why they called it plum pudding is that it was his way of illustrating an analogy. At the time, plum pudding was a popular English dessert. Basically, think of like a blueberry muffin. Inside of the doughy part of the muffin are little blueberries, and he suggested all these little blueberries were the negative parts, and he suggested the doughy part, is positive. So that's a new model of the atom. It happened in about 1897, and it was not a bad model. Based on what he knew at the time, it made total logical sense because he had now discovered, for the first time, a subatomic particle, the electron. Now, we've already slightly discussed Robert Millikan, but I need to bring back his work again here, because it wasn't until 1909, that Robert Millikan did what's known as the Millikan oil drop experiment. And this was key. This was really important because it helped solve a couple of puzzles. If you remember back on this previous slide here, all that Thomson was able to do was solve for a charge to mass ratio. He had the ability to calculate a velocity, a radius, and a field strength, but he had no idea how to calculate a charge or a mass. Well, in 1909, Robert Millikan discovered how to solve for the charge of these subatomic particles. If you remember doing this earlier in the year, what he did is he sprayed oil droplets and made them charge such that the oil droplet right here, it would normally want to fall down due to gravity, but because he set up these plates with a voltage between them, an electric force would want to pull it back up. And literally, this particle would hover in midair, right? It would just levitate in a way, right? He then would notice when the particle was hovering, and he realized that the electric force was equal to the gravitational force. The electric force was charge times field strength. Gravitational force was mass times gravity. By knowing that the electric field could be found by finding the voltage and the distance between these plates, he was then able to make this formula here. The charge of any particle sitting in between here would have been equal to mass times gravity, the distance between the plates, multiplied by the voltage between them. He was then able to find the charge of a particle. That was really important. One of the reasons why is that if there was an already known charge to mass ratio, but you didn't know charge and you didn't know mass, if you now do know charge, now you know mass. And that allowed them to then calculate the mass of electrons, subatomic particles. And that really confirmed it, because when they could find the mass of hydrogen or helium or lithium, and then they now found the mass of these corpuscles, electrons, and they realized that the mass of these electrons was to the minus 31, they recognized that, yes, subatomic particles definitely exist. So I've got some more notes about Robert Millikan. He discovered that all charges seem to be multiples of 1.6 times 10 to the minus 19. He didn't necessarily get 1.6 to the minus 19. He might have gotten 3.2 to the minus 19. He might have gotten 4.8 to the minus 19. He realized, though, that if they were always multiples of 1.6, that this had 2 electrons and this one had 3 electrons, because 1 electron would be 1.6. And so we now call that, as we've learned, the elementary charge, which is the letter E. And this is the really key thing here. This allowed them to then calculate the mass of the electron, because the charge to mass ratio puzzle had now been solved. Quick recap here. 1897, J.J. Thomson figures out a way to find this charge to mass ratio right here by finding the velocity of these electrons. He called them corpuscles after he called them cathode rays. He found the velocity of the electrons getting accelerated through this tube. Here's how he found that velocity. Then he managed to use that velocity to find a charge to mass ratio. He recognized that the ratio was much bigger than anything he'd ever seen before. The reason why it was so big is that the mass of the electron was so incredibly tiny. It was 1,000 times off of anything he'd ever seen before. I think I have that written somewhere here. Yeah, the charge to mass ratio was way bigger than any other ion they'd ever discovered before. So it was 1,000 times bigger. Because of this, he suggests his new model, the plum pudding model. That plum pudding model is a good idea, the idea of subatomic particles, but he had no idea how big they were, because he could only get to a charge to mass ratio. Once Robert Millikan figures out how to solve for charge, as soon as you can plug charge into this equation up here, then you can solve for mass. And like I'm finishing off with right here, now scientists knew that the electron had a mass of 9.11 times 10 to the minus 31. Definitive proof that subatomic particles exist. Any questions so far? In the same year, 1909, Ernest Rutherford is working on another experiment. And he was also curious about what these atoms were made of. Because at this time, Thomson had more or less conclusively proven that particles were no longer indivisible. This whole idea of particles basically being a billiard ball that you cannot cut in half seems to be false. And so Rutherford is trying to figure out, well, what's inside these things? And so he, along with Geiger and Marsden, made what's known as his gold foil experiment. From what I understand, Rutherford actually isn't the one who did the experiment. It was actually Geiger and Marsden, who were like his undergrad students, I guess, something along those lines. And he was just the supervisor, so I guess he gets to have his name attached to it, even though these guys did all the work. One of the reasons I point that out, I can understand why Rutherford didn't do the experiment itself. In order to do it, they had to use a radioactive sample of radium. So I can understand why he may be more inclined to be the big boss and say, hey, you undergrads, you go do the experiment. I'm going to hang out over here where there's no radioactive energy, So I thought that was kind of cool. What he ended up doing basically is he set up a radioactive sample of radium. And we're going to learn about this later on in this unit, but it was undergoing decay. And so it was giving off radiation through a decay process. And as it decayed, it shot alpha particles in one direction. We're going to focus on the decay part of this in a future lesson. So if I could leave that for now. But all you need to basically understand is that particles that have like a huge amount of parts to them, they can actually split up so that what ends up happening is like a few parts of them like come off. It's basically like fission and fusion, where you can actually take the nucleus of atoms and either bring them together, that's fusion, or fission is where you split a nucleus apart. We now know about the nucleus. Rutherford had no clue there was a nucleus until this experiment, but that's effectively what was happening is through radioactive decay, an alpha particle was being shot off. So just go with that for now. He shot the alpha particle towards a sheet of gold foil. And on the other side of the foil, there was some zinc sulfide. And what ends up happening is whenever zinc sulfide is hit by alpha particles, it glows. And so basically, as he shot these particles at gold foil, if the particles went through the gold, they would then make light hit on the other side. Now, at first, Rutherford assumed that alpha particles would phase right through the atoms. He had good reason to believe that. According to Thomson's model of the atom, which I had right here, if all of these little corpuscles, which we now know as electrons, if there were subatomic bits inside and there was like a fluid that was positively charged, in theory, then bits should be able to phase right through. That's what he figured. But what happened was completely unexpected to him. So here again is a picture of what happened. Inside this lead box is basically radioactive material. Radioactive material is being shot in all directions. Fortunately, it's inside a lead box, and so in theory, that should protect these scientists. Except for randomly, once in a while, a particle would get shot out this way. It's an alpha particle, which is, if you remember, alpha particles have 4, 2 as their notation. The 4 is because there's 4 subatomic particles in the nucleus. There's actually 2 protons and 2 neutrons. And the 2 and 2, they add up to this 4 right here. This 2 right here refers to the fact that there's 2 protons. Are you guys familiar with that, by the way? Maybe I should pause on that. You guys know this notation where the top number is the mass number and the bottom number is the atomic number? You guys learned that at some point before? Okay, quick mini lesson just in case you're not. If I were to ever give you something like oxygen 812, this would mean that oxygen has 8 protons, 8 being the bottom number down here. And this is a really weird isotope. I guess it would have to have 4 neutrons because 8 and 4 adds up to 12. Okay, hopefully you've seen that notation before. They didn't know about this at the time, though. Keep in mind, I'm explaining something that we now know in hindsight, but at the time, they had no idea about protons and neutrons. So, anyways, Rutherford shoots these alpha particles at this sheet of gold foil, and he would expect them to basically go straight through. He expected them to phase through. But what ended up happening is many of them were deflected at small angles and some at very large angles. So what ended up happening is they were actually bouncing kind of off to the sides. He wanted them all to show up right here. He expected all of the flashes of light to occur right here, but like he'd see one over there and over there and over there. And that made no sense. How does this particle all of a sudden bounce off to the sides? Here's the even strangest thing. Some alpha particles ended up getting deflected backwards towards him. When he made this like ring of the zinc sulfide and made it large enough to go all the way around, he discovered that some of these particles were actually deflecting right back towards you. And I love this quote. In Rutherford's journal, here's the phrasing he used. He said, "This was strange. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." So basically, he's talking like artillery in war. You're firing this big, I don't know, rocket kind of thing, right? You fire it at Kleenex. And it doesn't phase through the Kleenex. It doesn't just bounce off to the side. It hits Kleenex and bounces back at you. He could not explain why this happened according to this model right here. Because according to this model right here, that wouldn't make sense. So it led him to make a new model of the atom. Let me show you one more picture here, though. So again, here's the lead covering a radioactive material. The radioactive material spits out alpha particles. Most of them were supposed to go to right here. A few go this way, a few go this way, and a few bounce off at really weird angles, including right back at you, and he couldn't really explain it until he came up with a new idea for a model of an atom. And it's known as the Rutherford model. Sometimes it's called the planetary model. The biggest difference is this word right here. Rutherford coined the term nucleus. He suggested that maybe all of this positive fluid that Thomson hypothesized, maybe that positive fluid isn't over the course of the entire atom. Maybe it's localized or centralized, right in the very, very middle. And so he shrunk down the atom to some degree. The main difference is rather than the electrons being inside this ball or sphere, what he suggested is maybe that this ball or sphere is actually really tiny in the middle and all of the electrons are around it. That's the fundamental change. The electrons are no longer inside the atom. The electrons are outside the atom because the atom itself is actually really tiny, and he called that the nucleus. This then explains why things would deflect. I've got a good picture here. As these alpha particles would bounce through these atoms, sometimes they would hit the side of the nucleus and deflect a little bit. Sometimes they would go right through because they missed the nucleus entirely. This one here would bounce a little bit off to the side. And what if it hit like straight on? What if this alpha particle hit straight on the nucleus? That could explain why it would bounce right back at you. And so it seemed logical. That was his theory. He didn't really necessarily have the ability to see a nucleus. Again, microscopes didn't exist to the point where you could actually zoom in that close. But evidence seemed to suggest that the mass, remember how we talked about, oh, that's a horrible M. Remember how we talked about how they were trying to solve for mass in the charge to mass ratio? He suggested then that all of the mass must be hidden inside this nucleus right here. So this is how we often draw the model of Rutherford's. We often call it the planetary model, and the reason we do that is because he suggested that this was kind of like our solar system. He suggested that in a way, what if the sun is like this nucleus, and all of the electrons are orbiting around it, kind of like in these sorts of concentric loops. They're actually drawn in ellipses. If you guys remember in Physics 20, you would have learned that according to Kepler, planets actually orbit in ellipses. So sometimes we draw these in elliptical orbits, and this is a planetary model. What he suggested then is that there's a concentrated positive charge right in the middle, and that explains why the alpha particle had such an extensive deflection, called the planetary model. At the time, by the way, neutrons were actually still undiscovered. Nobody had realized that neutrons exist yet. You have to give me a sec here, hang on. Yes. Okay. Sure. Okay, sorry guys. I'm almost done. Our lesson is just about finished here. So Rutherford has this new idea, decides that now there's a nucleus in the middle. As his way of illustrating it, because he has no way of seeing it, as his way of illustrating it, he suggests that it's like the universe. It's like our planets. And so this electron would be like Earth going around the sun. This electron here would be like Jupiter going around the sun. This electron would be like Saturn going around the sun. He suggests that that's the case. However, here's one of the cool things I like about this story. He actually knew his model was incorrect. Although it's the best he could come up with, he actually knew at the time that he had a huge flaw. And so he wasn't going around bragging, saying, like, guys, I've solved the problem. All he was doing was saying, I think I have a slightly better understanding of things, but here's his flaw. He knew that if electrons were moving in a circle, circular electrons would then have a centripetal acceleration. Remember how when things are going in a circle from Physics 20, they would be a centripetal acceleration? And one of the things that we learned in our previous unit is anytime that you have acceleration of charges, there should be EMR given off. Because that's what Maxwell and Hertz discovered, is that if you accelerate electrons, accelerating electrons should be giving off electromagnetic radiation. This then causes a huge problem because two things would happen. First of all matter in the universe would then be, guys, shush. All matter in the universe would be giving off EMR. I mean, whether it's radio waves or microwaves or ultraviolet rays, it literally means that everybody would be giving off waves of some type. And then two, if things were giving off waves of energy, they would in theory be losing energy. And this is what should happen. If things were truly orbiting in a circle, this thing right here, as it undergoes centripetal acceleration, it's accelerating charge. Accelerating charges give off EMR, it would give off a wave. But as it would lose energy, eventually the electron would spiral into the middle and crash and burn into the nucleus, which would then render his whole theory irrelevant because now you don't have these electrons outside of the nucleus anymore. So he actually knew that his model was incorrect in 1909 when he suggested it. What's kind of cool, though, is that it didn't happen for very much longer. Tomorrow we're going to talk about Bohr's model of the atom. Bohr's model of the atom usually happens around 1913. And so it was only a few years later that Bohr suggested a solution to this problem. But that's kind of where I'm going to leave this, kind of on a bit of a cliffhanger, is that Rutherford has this great idea of a nucleus, but he knows that the electrons can't actually be going in circles in the same way that planets do. He couldn't figure out what exactly the electrons were doing. He knew the electrons must be outside of the nucleus. The nucleus must be this dense, concentrated matter, but he had no idea what are those electrons doing. Here's the cool thing. We're still not really sure what the electrons are doing, because as soon as we try to look for the electrons, remember Heisenberg's uncertainty principle? As soon as you try to know more about their position, you know less about their momentum. And as soon as you know more about their momentum, you know less about their position. And so even to this day, with the whole concept of wave-particle duality, we really have a hard time of trying to understand where are the electrons. And that's where we're going to go over the next couple of classes. I'm going to go back to the beginning of my slide here. This is the timeline I need you guys to know about. Again, it's more of like a social studies sort of history lesson. We've now covered Dalton, Thomson, and Rutherford. Tomorrow we're going to talk about the Bohr model and how Bohr managed to solve Rutherford's problem. And then we're going to finish off by talking about the quantum model, which is kind of our most recent theory. It's often known as the cloud model, which is post-1930. And then after we do that, that's why I'm going to show you this video, because I think the video does a pretty good job of trying to explain how this cloud model of electrons fits best. So, okay, that's kind of my lesson for the day. Does anybody have any questions? Was large parts of this review from stuff you've learned at a previous time? Okay. What I need you guys to know is the accomplishments of the scientists, but maybe more importantly, you need to understand the formulas that they worked with here. These formulas right here, the velocity selector formula, the charge to mass ratio formula, as well as the Millikan oil drop formula. I need you to know like what those things helped accomplish, like what the point of those was. Okay, one last thought, and then I'll stop for the day. If you go to my website and look at the assignments that I have posted, I'm just going to find a PDF here in my notes. Some of the questions that I'm going to ask you to work on the assignments are really more like almost writing an essay, to be honest. It's going to be a little bit different in terms of how you're going to answer it. Okay. I'd like to point out this question right here. This is one of the questions I'm going to ask you to do. So here's one of them. It says, scientific theories are constantly being revised. Sometimes a new theory is inconsistent with an existing theory. In other cases, new observations are made that cannot be explained by an existing theory. In either situation, the existing theory has to be revised or replaced. This is actually exactly what we're talking about right now. Rutherford's planetary model of the atom was revised for two reasons. I've actually talked about one of them already. One of the reasons is that it was inconsistent with Maxwell's theory of electromagnetism. And by that I mean Maxwell recognized that accelerating charges should be losing energy due to EMR. There's actually another reason why the theory was inconsistent. We're going to talk about it tomorrow. It's something called line spectrum. This question right here then basically asks you kind of in like a mini essay to describe what led to Rutherford's planetary model needing to be revised, including identify what were the features of the planetary model, why revisions were required based on a couple of these ideas, and then identify the main features of the new atomic model. So anyways, I just want to point out this question here because it's more of like an essay, an explain what happened in history kind of question. So, okay, let me stop my recording here and then I'll give you guys some last thoughts and you can go.